Okay, I'm going to be reading the article Quantum Mechanics out loud. Quantum Mechanics, a good article from Wikipedia, the Free Encyclopedia. For a more accessible and less technical introduction to this topic, see Introduction to Quantum Mechanics. Quantum Realm redirects here for the fictional location of the Marvel Cinematic Universe. See Quantum Realm. Quantum mechanics is a fundamental theorem of physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. It is the foundation of all quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. Classical physics, the collection of theories that existed before the advent of quantum mechanics, describes many aspects of nature at an ordinary macroscopic scale, but it is not sufficient for describing them at small atomic or subatomic scales. Most theories in classical physics can be derived from quantum mechanics as an approximation valid at large macroscopic scale. Quantum mechanics differs from classical physics in that energy, momentum, angular momentum, and other quantities of a bound system are restricted to discrete values. Quantization objects have characteristics of both particles and waves, wave-particle duality. And there are limits to how accurately the value of a physical quantity can be predicted prior to a measurement, given a complete set of initial conditions, the uncertainty principle. Quantum mechanics rose gradually from theories to explain observations which could not be reconciled with classical physics, such as Max Planck's solution in 1900 to the black body radiation problem and the correspondence between energy and frequency in Albert Einstein's 1905 paper, which explained the photoelectric effect. These early attempts to understand microscopic phenomena, now known as the old quantum theory, led to the full development of quantum mechanics in the mid-1920s by Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, Paul Dirac, and others. The modern theory is formulated in various specially developed mathematical formalisms. In one of them, a mathematical entity called the wave function provides information in the form of probability amplitudes about what measurements of a particle's energy, momentum, and other physical properties may yield. Overview and fundamental concepts. Quantum mechanics allows the calculation of properties and behavior of physical systems. It is typically applied to microscopic systems, molecules, atoms, and subatomic particles. It has been demonstrated to hold true for complex molecules with thousands of atoms, but its application to human beings raises philosophical questions such as Wigner's friend. What's that? Wigner's friend. Wigner's friend is a thought experiment in theoretical quantum physics first conceived by the physicist Eugene Wigner in 1961 and further developed by David Deutsch in 1985. The scenario involves an indirect observation of a quantum measurement. An observer W observes another observer F who performs a quantum measurement of a physical system. The two observers then formulate a statement about the physical system state after the measurement according to the laws of quantum theory. However, in most interpretations of quantum theory, the resulting statements of the two observers contradict each other. This reflects the seeming incompatibility of two laws in quantum theory, the deterministic and continuous time evolution of the state of a closed system and the non-deterministic discontinuous collapse of the state of a system upon measurement. Wigner's friend is therefore directly linked to the measurement problem in quantum mechanics with its famous Schrödinger's cat paradox. Generalizations and extensions of Wigner's friend have been proposed. Two such scenarios involving multiple friends have been implemented in the laboratory using photons to stand in for the friends. Alright, where was I? But its application to human beings raises philosophical problems such as Wigner's friend, and its application to the Earth as a whole remains speculative. Predictions of quantum mechanics have been verified experimentally to an extremely high degree of accuracy. A fundamental feature of the theory is that it usually cannot predict certainly what will happen, but only give probabilities. Mathematically, a probability is found by taking the square of the absolute value of a complex number known as a probability amplitude. This is known as the Born rule, named after the physicist Max Born. For example, a quantum particle like an electron can be described by a wave function which associates to each point in space a probability amplitude. Applying the Born rule to these amplitudes gives a probability density function for the position that an electron will be found to have when an experiment is performed to measure it. This is the best the theory can do. It cannot say for certain where the electron will be found. The Schrödinger equation relates the collection of probability amplitudes that pertain to one moment of time to the collection of probability amplitudes that pertain to another. One consequence of the mathematical rules of quantum mechanics is a trade-off in predictability between different measurable quantities. The most famous of this uncertainty principle says that no matter how a quantum particle is prepared or how carefully experiments upon it are arranged, it is impossible to have a precise prediction for a measurement of its position and also at the same time for a measurement of its momentum. Another consequence of the mathematical rules of quantum mechanics is the phenomenon of quantum interference, which is often illustrated with the double-slit experiment. In the basic version of this experiment, a coherent light source such as a laser beam illuminates a plate pierced by two parallel slits, and the light passing through the slits is observed on a screen behind the plate. The wave nature of light causes the light passing through the two slits to interfere, producing bright and dark bands on the screen a result that would not be expected if light consisted of classical particles. However, the light is always found to be absorbed at the screen at discrete points as individual particles rather than waves. The interference pattern appears via the varying density of these particle hits on the screen. Furthermore, versions of the experiment that include detectors at the slits find that each detected photon passes through one slit as would a classical particle and not through both slits as would a wave. Furthermore, such experiments demonstrate that particles do not form the interference pattern if one detects which slit they pass through. Other atomic scale entities, such as electrons, are found to exhibit the same behavior when fired towards a double slit. This behavior is known as wave-particle duality. Another counterintuitive phenomenon predicted by quantum mechanics is quantum tunneling. A particle that goes up against the potential barrier can cross it, even if its kinetic energy is smaller than the maximum of the potential. In classical mechanics, this particle would be trapped. Quantum tunneling has several important consequences, enabling radioactive decay, nuclear fusion in stars, and applications such as scanning, tunneling, microscopy, and tunnel diode. When quantum systems interact, the result can be the creation of quantum entanglement. Their properties become so intertwined that a description of the whole solely in terms of the individual parts is no longer possible. Erwin Schrödinger called entanglement the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Quantum entanglement enables the counterintuitive properties of quantum pseudo-telepathy and can be a valuable resource in communication protocols such as the quantum key distribution and superdense cooling. Contrary to popular misconception, entanglement does not allow sending signals faster than light, as demonstrated by the no communication theorem. Another possibility opened up by entanglement is testing for hidden variables, hypothetical properties more fundamental than the quantities addressed in quantum theory itself, knowledge of which would allow more exact predictions than quantum theory can provide. A collection of results, most significantly Bell's theorem, have demonstrated that broad classes of such hidden variables are in fact incompatible with quantum physics. According to Bell's theorem, if nature actually operates in accord with any theory of local hidden variables, then the results of a Bell test will be constrained in a particular quantifiable way. Many Bell tests have been performed using entangled particles, and they have shown results incompatible with the constraints imposed by local hidden variables. It is not possible to present these concepts in a more superficial way without introducing the actual mathematics involved. Understanding quantum mechanics requires not only manipulating complex numbers, but also linear algebra, differential equations, group theory, and other more advanced subjects. Accordingly, this article will present a mathematical formulation of quantum mechanics and survey its application to some useful and oft studied examples. Mathematical formulation. Now, there's a main article, Mathematical Formulation of Quantum Mechanics, that goes in depth into this. But anyways, in the mathematically rigorous definition of quantum mechanics, the state of a quantum mechanical system is a vector omega. Is that psi? Of a wave function belonging to a separable complex Hilbert space H. This vector is postulated to be normalized under the Hilbert space inner product. That is, it obeys equals 1. It is well defined up to a complex number of modulus 1. The global phase, that is, represent the same physical system. In other words, the possible states are points in the projective space of a Hilbert space, usually called the complex projective space. The exact nature of this Hilbert space is dependent on the system. For example, for describing position and momentum, the Hilbert space is the space of complex square integratable functions. L2 of complex, while the Hilbert space with the spin of a single proton is simply the space of two-dimensional complex vectors C2 with the usual inner product. Physical quantities of interest, position, momentum, energy, spin are represented by observables, which are Hermitian, more precisely self-adjoint linear operators acting on the Hilbert space. A quantum state can be an eigenvector of an observable, in which case it is called an eigenstate, and the associated eigenvalue corresponds to the value of the observable in that eigenstate. More generally, a quantum state will be a linear combination of the eigenstates known as quantum superposition. When an observable is measured, the result will be one of its eigenvalues with the probability given by the Bohr rule. In the simplest case, the eigenvalue lambda is non-degenerate, and the probability is given by where it is its associated eigenvector. More generally, the eigenvalue is degenerate, and the probability is given by where p lambda is the projector onto its associated eigenspace. In the continuous case, these formulas give instead the probability density. After the measurement, if result lambda was obtained, the quantum state is postulated to collapse to lambda vector in the non-degenerate case, or to p base lambda, all that in the general case. The probabilistic nature of mechanics thus stems from the act of measurement. This is one of the most difficult aspects of quantum systems to understand. It was a central topic in the famous Bohr-Einstein debates in which two scientists attempted to clarify these fundamental principles by way of thought experiments. In the decades after the formulation of quantum mechanics, the question of what constitutes a measurement has been extensively studied. Newer interpretations of quantum mechanics have been formulated that do away with the concept of wave function collapse. See, for example, the many worlds interpretation. The basic idea is that when a quantum system interacts with a measuring apparatus, their respective wave functions become entangled so that the original quantum system ceases to exist as an independent entity. For details, see the article on measurements in quantum mechanics. The time evolution of a quantum state is described by the Schrödinger equation, where H denotes the Hamiltonian, the observable corresponding to the total energy of the system, and H is the reduced Planck constant. The constant IH is introduced so the Hamiltonian is reduced to the classical Hamiltonian. In cases where the quantum system can be approximated by a classical system, the ability to make such an approximation in certain limits is called the correspondence principle. The solution of this differential equation is given by the operator U of t is known as the time evolution operator and has the crucial property that it is unitary. This time evolution is deterministic in the sense that given an initial quantum state of 0, it makes a definite prediction of what the quantum state will be at any later time. Some wave functions predict probability distributions that are independent of time, such as eigenstates of the Hamiltonian. Many systems are treated dynamically in classical mechanics are described as such static wave functions. For example, a single electron in an unexcited atom is pictured classically as a particle moving around a circular trajectory around the atomic nucleus, whereas in quantum mechanics it is described by a static wave function surrounding the nucleus. For example, the electron wave function for an unexcited hydrogen atom is a spherically symmetric function known as an s orbital. Analytic solutions of the Schrödinger equation are known for very few relatively simple model Hamiltonians, including the quantum harmonic oscillator, the particle in a box, the dihydrogen cation, and the hydrogen atom. Even the helium atom, which contains just 2 electrons, has defied all attempts at a fully analytic treatment. However, there are techniques for finding approximate solutions. One method, called perturbation theory, uses the analytic result for a simple quantum mechanical model to create a result for a related but more complicated model by, for example, the addition of a weak potential energy. Another method is called semi-classical equation of motion, which applies to systems for which quantum mechanics produces only small deviations from classical behavior. These deviations can then be computed based on the classical motion. The approach is particularly important in the field of quantum chaos. Uncertainty principle. One consequence of the basic quantum formalism is the uncertainty principle. In its most familiar form, this states that no preparation of a quantum particle can imply simultaneously precise predictions both for a measurement of its position and for a measurement of its momentum. Both position and momentum are observable, as meaning they are represented by Hermitian operators. The position operator x hat and the momentum operator p hat do not commute, but rather satisfy the canonical commutation relation x hat p hat equals I hat. Given a quantum state, the Bohr rule lets us compute expectation values for both x and p, and moreover for powers of them. Defining the uncertainty for an observable as standard deviation we have, and likewise for the momentum, the uncertainty principle states that either standard deviation can in principle be made arbitrarily small, but not both simultaneously. This inequality generalizes to arbitrary pairs of self-adjoint operators A and B. The commutator of these two operators is AB minus BA, and this provides the lower bound on the product of standard deviations. Another consequence of the canonical commutation relation is that the position and momentum operators are Fourier transforms of each other, so the description of an object according to its momentum is the Fourier transform of its description according to its position. The fact that dependence in momentum is the Fourier transform of the dependence in position means that the momentum operator is equivalent up to an I divided by h bar factor to taking the derivative according to the position, since in Fourier analysis differentiation corresponds to multiplication in the dual space. This is why in quantum equations in position spaces the momentum p is replaced by negative h, and particularly the non-relativistic Schrödinger equation position space, the momentum squared term is replaced with the Laplacian times that. Composite systems and entanglement. Okay, I'll almost do the math part. When two different quantum states are considered together, the Hilbert space of the combined system is the tensor product of the Hilbert spaces of the two components. For example, A and B be two quantum systems with Hilbert spaces A and HB respectively. The Hilbert space of the composite system is then the tensor product of HA and HB. If the state for the first system is the vector A and second is this, then the state is not all states in the joint Hilbert space can be written in this form, however, because the superposition principle implies that linear combinations of these separable or product states are also valid. For example, if are both possible states for system A, and likewise are possible states for system B, then is a valid joint state that is not separable. States that are not separable are called entangled. If the state for a composite system is entangled, it is impossible to describe either component system A or system B by a state vector. One can instead define reduced density matrices that describe the statistics that can be obtained by making measurements on either component system alone. This necessarily causes the loss of information, though knowing the reduced density matrices of the individual systems is not enough to reconstruct the state of the composite system. Just as density matrices specify the state of a subsystem of a larger system, analogously, positive operator value measurements (POVMs) describe the effect on a subsystem of a measurement performed on a larger system. POVMs are used extensively in quantum information theory. As described above, entanglement is a key feature of models of measurement processes in which an apparatus becomes entangled with the system being measured. Systems interacting with the environment in which they reside generally become entangled with that environment, a phenomenon known as quantum decoherence. This can explain why in practice quantum effects are difficult to observe in systems larger than microscopic. Equivalence between formulations. There are many mathematically equivalent formulations of quantum mechanics. One of the oldest and most common is the transformation theory proposed by Paul Dirac, which unifies and generalizes the two earliest foundations formulations of quantum mechanics: matrix mechanics, invented by Werner Heisenberg, and wave mechanics, invented by Erwin Schrödinger. An alternative formulation of quantum mechanics is Feynman's path integral formulation, in which a quantum mechanical amplitude is considered as the sum over all possible classical and non-classical paths between the initial and final states. This is the quantum mechanical counterpart of the action principle in classical mechanics. Symmetries and conservation laws. The Hamiltonian is known as the generator of time evolution since it defines a unitary time operator for each value of t. From this relation between u of t and h, it follows that any observable a that commutes with h will be conserved. Its expectation value will not change over time. This statement generalizes mathematically any Hermitian operator a can generate a family of unitary operators parameterized by a variable t. Under the evolution generated by a, any observable b that commutes with a will be conserved. Moreover, if b is conserved by evolution under a, then a is conserved under the evolution generated by b. This implies a quantum version of the result proven by Emmy Noether and classical Lagrangian mechanics. For every differentiable symmetry of a Hamiltonian, there exists a corresponding conservation law. Okay, now we're going to do some examples. Examples: free particle. The simplest example of quantum systems with a position degree of freedom is a free particle in a single spatial dimension. A free particle is one which is not subject to external influences, so its Hamiltonian consists only of its kinetic energy h equals 1 divided by 2m times p squared equals negative h squared over 2m times d squared over dx squared. The general solution to the Schrödinger equation is given by x of t equals 1 over the square root of 2 pi times the integral from negative infinity to infinity times this wave function hat of k and 0 times e to the power of I times kx minus h bar times k squared over t over 2m times t dk, which is a superposition of all possible plane waves e to the power of I kx minus h bar k squared over 2mt, which are eigenstates of the momentum operator with momentum p equals h bar k. The coefficients of the superposition are the wave function hat k0, which is the Fourier transform of the initial state, the wave function x of 0. It is not possible for the solution to be a single momentum eigenstate or a single position eigenstate. These are not normalizable quantum states. Instead, we consider a Gaussian wave packet wave function with x and 0 equals 1 over the fourth root of pi times a e to the negative x squared over 2a, which has a Fourier transform and therefore momentum distribution x hat of k and 0 equals the fourth root of a over pi times e to the negative ak squared over 2. We see as we make a smaller, the spread in position gets smaller, but the spread in momentum gets larger. Conversely, by making a larger, we make the spread in momentum smaller, but the spread in position gets larger. This illustrates the uncertainty principle. As we let the Gaussian wave packet evolve in time, we see that its center moves through space at a constant velocity, like a classical particle with no forces acting on it. However, the wave packet will also spread out as time progresses, which means the position becomes more and more uncertain. The uncertainty in momentum, however, stays constant. This is the position space probability of a Gaussian wave packet traveling in one dimension in free space. So it looks like it's getting smaller. Okay, particle in a box. The particle in a one-dimensional potential energy box is the most mathematically simple example where restraints lead to the quantization of energy levels. The box is defined as having zero potential energy everywhere inside a certain region and therefore infinite potential energy outside that region. For the one-dimensional case in the x direction, the time-independent Schrödinger equation may be written negative h bar squared over 2m times d squared of the wave function dx squared equals e times the wave function. Is this psi okay, I just need to learn the name of this thing. What is the wave function? Position space. Kind of looks like a trident. Psi. Okay. Psi Greek. Where the differential operator is defined by p hat x, p sub x hat equals negative I times h bar times d dx. The previous equation is evocative of the classic kinetic energy analog 1 divided by 2m times p x hat squared equals E with the state psi, in this case having energy E coincident with the kinetic energy of the particle. The general solutions of the Schrodinger equation for the particle in the box are psi of x equals e to the power of I times kx plus b e to the power of negative plus b times e to the power of negative k times x, and E equals h bar squared times k squared divided by 2m, or from Euler's formula, psi of x equals c sine kx plus d cosine kx. The infinite potential walls of the box determine the values of c, d, and k at x equals 0 and x equals L, where psi must be 0. Thus, x equals 0, psi of 0 equals c sine of 0 plus d cosine of 0 equals d, and d equals 0 at x equals L. Psi of L equals 0 equals c sine kl, which c cannot be 0, as this would conflict with the postulate that psi has norm 1. Therefore, since sine k of L equals 0, kl must be an integer multiple of pi. K equals n times pi over L, n equals 1, 2, 3. This constraint on k implies a constraint on the energy levels, yielding E sub n equals h bar squared times pi squared times n squared over 2m. L squared equals n squared h squared over 8m L squared. A finite potential wall is a generalization of the infinite potential well problem to potential wells having finite depth. The finite potential well problem is mathematically more complicated than the infinite particle in a box problem, as the wave function is not pinned to zero at the walls of the well. Instead, the wave function must satisfy more complicated mathematical boundary conditions, as it is non-zero in regions outside the well. Another related problem is that of the rectangular potential barrier, which furnishes a model for the quantum tunneling effect that plays an important role in the performance of modern technologies such as flash memory and tunneling microscopy. I'm 22 minutes in. Harmonic oscillator. Main article, quantum harmonic oscillator. As in the classical case, the potential for the quantum harmonic oscillator is given by V of x equals 1/2 m times omega squared times x squared. This problem can be either treated by directly solving the Schrodinger equation, which is not trivial, or by using the more elegant latter method first proposed by Paul Dirac. The eigenstates are given by psi sub n of x equals the square root of 2 to the power of n times n factorial times m times omega divided by pi times h bar to the 1/4 power times e to the power of negative m times omega times x squared divided by 2 times h bar times h sub n of the square root of m times omega divided by h bar of x, where an n is equal to 0, 1, 2, etc., where h sub n are the Hermite polynomials. H sub n equals negative 1 to the n e to the power of x to the power of 2, and then d sub n, the nth derivative of e to the power of negative x squared, and the corresponding energy levels are E sub m equals h bar omega times m plus 1/2. This is another example illustrating the discretization of energy for bound states. Mach-Zehnder interferometer. The Mach-Zehnder interferometer. Yeah, I think I want to skip this one. We'll do applications. Applications. Quantum mechanics has had enormous success in explaining many of the features of our universe with regards to small scale and discrete quantities and interactions which cannot be explained by classical methods. Quantum mechanics is often the only theory that can reveal the individual behaviors of the subatomic particles that make up all forms of matter: electrons, protons, neutrons, photons, and others. Solid-state physics and material sciences are dependent upon quantum mechanics. In many aspects, modern technology operates at a scale where quantum effects are significant. Important applications of quantum theory include quantum chemistry, quantum optics, quantum computing, superconducting magnets, light-emitting diodes, the optical amplifier and the laser, the transistor, and semiconductors such as the microprocessor, medical and research imaging such as magnetic resonance imaging and electron microscopy. Explanations for many biological and physical phenomena are rooted in the nature of the chemical bond, most notably the macromolecule DNA. Relation to other scientific theories, classical mechanics. The rules of quantum mechanics assert that the state space of a system is a Hilbert space, and that observables of the system are Hermitian operators acting on vectors in that space, although they do not tell us which Hilbert space or which operates. They can be chosen appropriately in order to obtain a quantitative description of a quantum system, a necessary step in making physical predictions. An important guide for making these choices is the correspondence principle, a heuristic which states that the predictions of quantum mechanics reduce to those of classical mechanics in the regime of large quantum numbers. One can also start from an established classical model of a particular system and then try to guess the underlying quantum model that will give rise to the classical model and the correspondence limit. This approach is known as quantization. When quantum mechanics was originally formulated, it was applied to models whose correspondence limit was non-relativistic classical mechanics. For instance, the well-known model of the quantum harmonic oscillator uses an explicitly non-relativistic expression for the kinetic energy of the oscillator, and thus a quantum version of the classical harmonic oscillator. Complications arise with chaotic systems which do not have good quantum numbers, and quantum chaos studies the relationship between classical and quantum descriptions in these systems. Quantum decoherence is a mechanism through which quantum states lose coherence, thus became incapable of displaying many typically quantum effects. Quantum superpositions become simply probabilistic mixtures, and quantum entanglement becomes simply classical correlations. Quantum coherence is not typically evident at macroscopic scales, except maybe at temperatures approaching absolute zero, at which quantum behavior may manifest macroscopically. Many macroscopic properties of a classical system are a direct consequence of the quantum behavior of its parts. For example, the stability of bulk matter consisting of atoms and molecules which would quickly collapse under electrical forces alone, the rigidity of solids, and mechanical, thermal, chemical, optical, and magnetic properties of matter are all results of the interaction of electric charges under the rules of quantum mechanics. Special relativity and electrodynamics. Early attempts to merge quantum mechanics to special relativity involved the replacement of the Schrödinger equation with a covariant equation known such as the Gordon equation or the Dirac equation. While these theories were successful in explaining many experimental results, they had certain unsatisfactory qualities stemming from their neglect of the relativistic creation and annihilation of particles. A fully relativistic quantum theory required the development of quantum field theory, which applies quantization to a field rather than a fixed set of points. The first complete quantum field theory, quantum electrodynamics, provides a fully quantum description of the electromagnetic interaction. Quantum electrodynamics is, along with general relativity, one of the most accurate physical theories ever devised. The full apparatus of quantum field theory is often unnecessary for describing quantum electrodynamic systems. A simpler approach, one that has been used since the inception of quantum mechanics, is to treat charged particles as quantum mechanical objects being acted on by a classical electromagnetic force. For example, the elementary quantum model of the hydrogen atom describes the electric field of the hydrogen atom using a classical negative E squared divided by 4 pi times epsilon 0 r Coulomb potential. This semi-classical approach fails if quantum fluctuations in the electromagnetic field play an important role, such as in the emission of photons by charged particles. Quantum field theories of the strong nuclear force and the weak nuclear force have also been developed. The quantum field theory of the strong nuclear force is called quantum chromodynamics and describes the interactions of subnuclear particles such as quarks and gluons. The weak nuclear force and the electromagnetic force will unify in their quantized forms into a single quantum field theory known as electroweak theory by the physicists Abdus Salam, Sheldon Glasgow, and Steven Weinberg. Relation to general relativity. Even though the predictions of both quantum and general relativity have been supported by rigorous and repeated empirical evidence, their abstract formalisms contradict each other and have proven extremely difficult to incorporate into one consistent, cohesive model. Gravity is negligible in many areas of particle physics, so that unification between general relativity and quantum mechanics is not an urgent issue in those particular applications. However, the lack of a correct theory of quantum gravity is an important issue in physical cosmology and the search by physicists for an elegant theory of everything. Consequently, resolving the inconsistencies between both theories has been a major goal of both 20th century and 21st century physics. This theory would combine not only models of subatomic physics, but would also derive the four fundamental forces of nature from a single force or phenomenon. One proposal for doing so is string theory, which posits that the point-like particles of particle physics are replaced by one-dimensional objects called strings. String theory describes how these strings propagate through space and interact with each other. On distance scales larger than the string scale, a string looks just like an ordinary particle, with its mass, charge, and other properties determined by the vibrational state of the string. In string theory, one of the many vibrational states of the string corresponds to the graviton, a quantum mechanical particle that carries gravitational force. Another popular theory is loop quantum gravity, which describes quantum properties of gravity, and is thus a theory of quantum spacetime. LQG is an attempt to merge and adapt standard quantum mechanics and standard relativity. This theory describes space as an extremely fine fabric woven of finite loops called spin networks. The evolution of a spin network over time is called a spin foam. The characteristic length scale of a spin foam is the Planck length, approximately 1.16 times 10 to the minus 34 meters, and so lengths shorter than the Planck lengths are not physically meaningful at LQG. Philosophical implications. Since its inception, the many counterintuitive aspects and results of quantum mechanics have provoked strong philosophical debates and many interpretations. The arguments center on the probabilistic nature of quantum mechanics, the difficulties with wave function collapse, and the related measurement problem in quantum non-locality. Perhaps the only consensus that exists about these issues is that there is no consensus. Richard Feynman once said, "I think that I can safely say that nobody understands quantum mechanics." According to Steven Weinberg, there is now, in my opinion, no entirely satisfactory interpretation of quantum mechanics. The views of Niels Bohr, Werner Heisenberg, and other physicists are often grouped together as the Copenhagen interpretation. According to these views, the probabilistic nature of quantum mechanics is not a temporary feature which will eventually be replaced by a deterministic theory, but instead a final renunciation of the classical idea of causality. Both in particular emphasize that any well-defined application of the quantum mechanical formulation must always make reference to the experimental arrangement due to the complementary nature of evidence obtained under different experimental situations. Copenhagen-type interpretations remain popular in the 21st century. Albert Einstein, one of the founders of quantum theory, was troubled by its apparent failure to respect some cherished metaphysical properties such as determinism and locality. Einstein's long-running exchanges with Bohr about the meaning and status of quantum mechanics are now known as the Bohr-Einstein debates. Einstein believed that underlying quantum mechanics must be a theory that explicitly forbids action at a distance. He argued that quantum mechanics was incomplete, a theory that was valid but not fundamental, analogous to how thermodynamics is valid, but the fundamental theory behind it is statistical mechanics. In 1935, Einstein and his collaborators Boris Podolsky and Nathan Rosen published an argument that the principle of locality implies the incompleteness of quantum mechanics, a thought experiment later termed the Einstein-Podolsky-Rosen paradox. In 1964, John Bell showed that EPR's principle of locality together with determinism was actually incompatible with quantum mechanics. The implied constraints and the correlations produced by distance systems, now known as Bell's inequalities, that can be violated by entangled particles. Since then, several experiments have been performed to obtain these correlations with the result that they do in fact violate Bell inequalities and thus falsify the conjunction of locality with determinism. Bohmian mechanics shows that it is possible to reformat quantum mechanics to make it deterministic at the price of making it explicitly non-local. It attributes not only a wave function to a physical system, but in addition a real position that evolves deterministically under a non-guiding local equation. The evolution of a physical system is given at all times with the Schrödinger equation together with the guiding equation. There is never a collapse of the wave function. This solves the measurement problem. Everett's many worlds interpretation, formulated in 1956, holds that all the possibilities described by quantum theory occur simultaneously in a multiverse composed of mostly independent parallel universes. This is a consequence of removing the axiom of the collapse of the wave packet. All possible states of the measurements of the measured system and the measuring apparatus together with the observer present in a real physical quantum superposition. While the multiverse is deterministic, we perceive non-deterministic behavior governed by probabilities because we don't observe the multiverse as a whole, but only one parallel universe at a time. Exactly how this is supposed to work has been the subject of much debate. Several attempts have been made to make sense of this and derive the Born rule with no consensus on whether they have been successful. Relational quantum mechanics appeared in the 1990s as a modern derivative of Copenhagen-type ideas, and Cubism was developed some years later. History. Quantum mechanics was developed in the early decades of the 20th century, driven by the need to explain phenomena that in some cases have been observed in earlier times. Scientific inquiry into the wave nature of light began in the 17th to the 18th century when scientists such as Robert Hooke, Christian Huygens, and Leonhard Euler proposed a wave theory of light based on experimental observations. In 1803, English polymath Thomas Young described the famous double-slit experiment. This experiment played a major role in the general acceptance of the wave theory of light. During the 19th century, chemical research by John Dalton and Amadeo Amagavero lent weight to the atomic theory of matter, an idea that James Clerk Maxwell, Ludwig Boltzmann, and others built upon to establish the kinetic theory of gases. The successes of kinetic theory gave further credence to the idea that matter is composed of atoms, yet the theory also had shortcomings that would only be resolved by the development of quantum mechanics. While the early conception of atoms from Greek philosophy have been that there are indivisible units, the word atom deriving from the Greek for uncuttable. The 19th century saw the formation of hypotheses about subatomic structure. One important discovery in that regard was Merrill Faraday's 1838 observation of a glow caused by an electrical discharge inside a glass tube containing gas at low pressure. Julius Blücher, Johann Wilhelm Hittorf, and Eugene Goldstein carried on and improved upon Faraday's works, leading to the identification of cathode rays, which J.J. Thomson found to consist of subatomic particles that he called electrons. The black-body radiation problem was discovered by Gustav Kirchhoff in 1859. In 1900, Max Planck proposed the hypothesis that energy is radiated and absorbed in discrete quanta or energy packets, yielding a calculation that precisely matched the observed patterns of black-body radiation. The word quantum derives from the Latin meaning how great or how much. According to Planck, quantities of energy could be thought of as divided into elements whose size E would be proportional to their frequency V, E equals hv, where h is Planck's constant. Planck cautiously insisted that this was only an aspect of the processes of absorption and emission, was not the physical reality of the radiation. In fact, he had considered his quantum mechanics hypothesis a mathematical trick to get the right answer rather than a sizable discovery. However, in 1905, Albert Einstein interpreted Planck's quantum hypothesis realistically and used it to explain the photoelectric effect in which shining light in certain materials can eject electrons from the material. Niels Bohr then developed Planck ideas about radiation into a model of the hydrogen atom that successfully predicted the spectral lines of hydrogen. Einstein further developed this idea to show that an electromagnetic wave such as light could also be described as a particle layer called the photon, with it a discrete amount of energy that depends on its frequency. In his article on the quantum theory of radiation, Einstein expanded on the definition between energy and matter to explain the absorption and emission of energy by atoms. Although overshadowed at the time by his general theory of relativity, this paper articulated the mechanism underlying the simulated emission of radiation, which became the basis of the laser. This phase is known as the old quantum theory. Never complete or self-consistent, the old quantum theory is rather a set of heuristic corrections to classical mechanics. The theory is now understood as a semi-classical approximation of modern classical quantum mechanics. Notable results from this period include, in addition to the work of Planck, Einstein, and Bohr mentioned above, Einstein, Pierre Deby's work on the specific heat of solids, Bohr and Henrik Johann van Leeuwen's proof that classical physics could not account for diamagnetism, and Arnold Sommerfeld's extension of the Bohr model to include special relativistic effects. In the mid-1920s, quantum mechanics was developed to become the standard formulation for atomic physics. In 1923, the French physicist Louis de Broglie put forth his theory of matter waves by stating that particles can exhibit wave characteristics and vice versa. Beginning on de Broglie's approach, modern quantum mechanics was born in 1925 when the German physicists Werner Heisenberg, Max Born, and Pascal Jordan developed matrix mechanics, and the Austrian physicist Erwin Schrödinger invented wave mechanics. Born introduced the probabilistic interpretation of Schrödinger's wave function in July 1926. Thus, the entire field of quantum mechanics emerged, leading to its wider acceptance at the Fifth Solvay Conference in 1927. By 1930, quantum mechanics had been further unified and formalized by David Hilbert, Paul Dirac, and John von Neumann, with greater emphasis on measurement, the statistical nature of our knowledge of reality, and philosophical speculation about the observer. It has since permeated many disciplines, including quantum chemistry, quantum electronics, quantum optics, and quantum information science. It also provides a useful framework for many features of the modern periodic table of elements, and describes the behaviors of atoms during chemical bonding and the flow of electrons in computer semiconductors, and therefore plays a crucial role in many modern technologies. While quantum mechanics was constructed to describe the world of the very small, it is also needed to explain some macroscopic phenomena such as superconductors and superfluids. Okay, this is the end of the Wikipedia article on quantum mechanics. I hope this was interesting.